Hello, Mr. Kitchen, Cobleskill, Richmondville High School Physics, and today we're going to continue on with our discussion of the characteristics of periodic waves. And everything that we work with today is going to be focused on what does it mean when waves are in phase with each other. So let's just start out with a definition. When we say two waves are in phase, that means the points on the wave have both the same amplitude and the same direction of motion. Recall that if we're talking about a transverse wave, our points on the wave, for example, might be moving up and down. And what we're looking for are 2 points that have the same height above or distance below the equilibrium position, but they also have to be moving in the same direction. When we talk about the length of a wave, we just call that the wavelength. And the wavelength is the distance between consecutive points that are in phase. So when we're trying to figure out the wavelength, first we got to find a couple points that are in phase, and if you've got a point that's in phase, well, with the next consecutive point, they're said to be a wavelength apart. The Greek letter L is the symbol that we're going to be using for wavelength. That's the Greek letter lambda, and you make it something like this. We don't use the letter L in physics very often. It looks too much like the number 1, so we're going to use the Greek L instead. Wavelength is the distance between consecutive points in phase. It is a distance, and in our SI system of units, we've said that time is always measured in seconds. Well, it turns out that distances are always going to be measured in meters. So lambda will be measured in meters. Now in your notes, I'd like you, I know this is a little bit busy here, but I'd like you to start out by drawing an equilibrium line, and then we're going to draw 2.5 waves. A wave is composed of a crest and a trough, and then you'll see we repeat. So crest, trough, that's one wave. There's 2 waves up to point that I've labeled Q, and then an additional half a wave. You can see I've also put dots on the wave, one right at the equilibrium position, and then halfway up, and then at the top of the crest, and halfway down at the equilibrium position, halfway into the trough, at the bottom of the trough, and so on. I've labeled those points A through. Well, if you do this properly, you should end up with the letter U. Now, the first thing that we've got to look at is the direction of motion of these points that are on the wave. In order to do that, we've got to give our wave itself a direction, and so I'd like to think of this wave as moving to the right. We'll add a little V and an arrow over here. Now let's take a look at a point, let's say point D. And if we're interested in point D, we know this is a transverse wave, so point D has to be moving up and down like this as the wave moves to the right. The question is, at this instant in time, is point D moving upward or is point D on the downward tack? Well, the way that we can figure this out is by peeking a little bit. You just look to the left and see what's coming up. So if we're at point D, what we can see is a crest is coming up. That in a short period of time, point D has to be up here at the top of the wave as the crest goes by. So point D must be moving upward at this instant in time. Now, let's take a look at point F, for example. Again, we're going to peek to the left a little bit. So even though F is in a trough, what's coming up? Well, the equilibrium position, and then point D, and then the crest of a wave. So point F is also moving upward. All right, so we can't tell whether it's just crests or troughs. We've got to look at what's coming up, and all these points have to be moving upward as the crest of the wave is approaching. Now, an example of a point that's moving downward is point H. If I take a look at point H over here and I peek to the left a little bit and I see what's coming up, a trough is coming up. So H must be moving downward because in a short period of time, H is going to be, well, in the trough. All right? So here's our direction of motion, or sometimes we say the direction of impending motion for this wave. Now what we're interested in is looking for some points that have the same amplitude and the same direction of impending motion. We're going to try and find points that are a wavelength apart. So if we start up here with point D, we've already identified that point D is moving upward. Point J has the same amplitude. It's essentially positive 1/2 the height of the wave. If we look at the direction of motion, though, of point J, we find out that point J is moving downward. If we peek to the left a little bit, we see a trough is coming up here, and so we'll put a little down arrow here for point J. So let's continue on. It's not point J, but point L. And point L is, well, in a corresponding spot on the wave, just like point D. We see K is the trough of a wave. L is moving upward here. So now what we've got are 2 points that have the same amplitude, the same direction of impending motion or motion, and they are consecutive points. L is the next point that has the same amplitude and direction of impending motion. Because of that, these points are a wavelength apart. So in our notes here, we can just put a little arrow in here and we'll say, okay, these points are a wavelength apart. Any set of points with the same amplitude and direction of impending motion is a wavelength apart. So point H is on the downward tack here. Point N has the same amplitude, but it's moving upward. Point P is moving downward. It is the next point, the consecutive point that's in phase. So these 2 points, H and P, are a wavelength apart. Now, a quick way to do wavelengths, as you might have figured out here, is to just take a look at points that are crest to crest. Or alternatively, you can do points that are trough to trough. For example, these 2 points down here are also a wavelength apart. If points are at the top of crests, obviously they have the same amplitude, the maximum amplitude, and if you want to think of it this way, there is nowhere to go but down from here. So both of these points have to have a direction of impending motion downward. And the opposite is true. G and O down here, they have the same amplitude. It happens to be a negative amplitude, but they're at their lowest point, so they must be moving upward. So a couple examples of pairs of points in phase. Well, we said D and L are in phase. We said that H and P are in phase. And if we want to throw in one more, we could say, well, crest to crest, C and K are in phase. What I'd like you to do in your notes is to list 2 more points that are in phase and add those to your notes paper for tomorrow, please. That's the ending of the video on the characteristics of periodic waves.